viewers, welcome to this video lecture series on analysis and design of algorithm. In this session I shall continue with the mathematical analysis for non-recursive algorithms. As a first example for the mathematical analysis for non-recursive, we had seen one example to determine whether all the elements in an array are distinct. So one more example also we shall see on this non-recursive analysis. The problem here is to find the number of binary digits in the binary representation of a positive decimal integer. So your input is a positive decimal integer. Suppose if you are taking a decimal value as 15, to write this decimal value in binary, you are writing in this manner, fine. If you are taking a decimal number as 14, then you are writing in this manner, okay, the binary value. How many bits you are using here in order to represent the binary value? For 15 you are using 4 bits. For this particular, 14 you are using 4 bits. That means 4 bits are sufficient for us to represent a decimal value, decimal number 14. 4 bits are sufficient for us to represent a decimal number 15. If you are using the decimal number 32, then with 4 bits you cannot represent in binary. You require more than 4 bits are needed in order to represent the decimal number 32. Using a decimal number 256. So this algorithm is basically counting what the number of bits that are used to represent a positive decimal number. For that the code is the pseudocode is here. Input is a positive decimal number and the output should be the number of binary digits in the nth representation. So if the output you are going to get some number here, 4 bits means the output will be 4. If your decimal value requires 6 bits or 8 bits, then the output is 8. So basically output is what? The number, the count of binary digits in the nth representation. So these are the 1, 2, 3, 4, 5. 5 steps are there for this algorithm. Because you want to count the number of bits, you are keeping a variable here, count, to keep track of the number of bits that are required in order to represent the decimal number. So we shall see this pseudocode with an example. We shall trace this and finally find out the time efficiency for this algorithm. Let me take n equal to 50. So now for this is the positive decimal integer. What is the first step? Your count is 1. Initially your count is 1. Okay, you have assigned it as 1. While n greater than 1, n is 15. Okay, is 15 greater than 1? Yes, it is true. If it is true, increase the count by 1. So your count becomes 2 now. Then whatever is the value for n, you divide by 2. Okay, you divide by 2. So your value for n is here 15. 15 divided by 2 is how much? 7.5. So take only the integer part. In this it is 7. So what you have to do is your updated value for n is now 7, the new value. Once again check whether the new value of n is greater than 1. 7, is it greater than 1? Yes, it is greater than 1. Then increase the count by 1. The new value of count is 3 now. Then follow this step, new value of n divide by 2. Now at present you are having n. So you will write 7 divided by 2. You will get 3.5. Take the integer part of it, it is 3. So the new value of 3 is, okay, the new value of n is 3. Return count statement refers to the updated value of the count here. Now your new value of n is 3. Is 3 greater than 1? Yes, it is greater than 1. If it is greater than 1, you increase the count by 1. Then you divide that n value by 2. So now you are having 3 divided by 2. So how much you will get? 1.5. Take the integer part. Integer part is here 1. So your new value of 1 is now, okay, new value of n is 1. And then you check whether this n is greater than, n is 1. 1 greater than 1? No. The condition is false. Here. If the condition is false, then it will not enter into the loop. This count statement will not get executed. So finally, what is that you have observed? For a value of n equal to 15, okay, you found that for a value of n equal to 15, the count that is appearing here is 4. Whatever is the count here, the updated value at the end for the count variable, in this case we have 4, that becomes what? The number of bits, the number of binary digits used to represent a positive decimal integer. So given was 15, and to represent this 15 in the binary, you are writing like this. So 4 binary digits are required. So that is what we got here, the updated value for the count. Return count refers to this one. The number of comparisons that are done here is 4. Because even though for the fourth comparison this count statement did not get executed, but still you have to include because you had tested it. So n greater than 1 got executed, but the condition became false and this statement did not get executed. If you observe here in this example, the updation of the variable count is happening 3 times. Okay, whereas the comparison statement n greater than 1 is happening 4 times. Here comparison statement is the one that is getting executed maximum number of times. Number of comparisons that are carried out for such an algorithm is log to the base 2n plus 1. Okay, and the time efficiency for this algorithm is, what is n here? N is representing the positive decimal integer. So the time efficiency for this algorithm is P of n equal to big O of log to the base 2 n. N is what? N is the positive decimal integer. So this is a very simple algorithm wherein I have taken n equal to 15. You can try out for a higher value also, n equal to 256. Fine. And check how many number of times this comparison statement gets executed, how many number of times the count variable gets updated, how many and what is the return value for the count, so that gives you the number of binary digits that is used to represent the decimal number, given decimal number. So that's it in this session. Hope you find this session useful. If you find it useful, please like, share and subscribe to my channel. Thank you. Bye bye and take care.